Hello and welcome to my Pre-Algebra Big Ideas review series. This video covers Chapter 8, Section 4, titled Surface Areas and Volumes of Similar Solids. Similar solids are solids that have the same shape and proportional corresponding dimensions. By the end of this video, you will be able to identify similar solids and find missing measures of similar solids. With that, you'll be reviewing surface area in general and finding surface areas and determining volumes of similar solids. Please leave a like if you find this video to be helpful. Give your classmates a heads up too. It will more than likely help them, and it certainly will help this channel to be seen by more students. If you would like me to cover any of these topics in greater detail, please leave a comment in the comment section below. I read them and do my best to address each as time permits. Please subscribe to my channel and ring the bell icon to be notified every time I release a new video. Thank you. Let's get doing some math. So example 1, identifying similar solids. Similar solids are solids that have the same shape and proportional corresponding dimensions. Which cylinder is similar to cylinder A? So cylinder A and cylinder B, and then we do cylinder A and cylinder C, and we're going to do the comparisons. But you see there are these similars here. First we have cylinder A, which has a 4-inch height and a 4-meter height and a 6-meter radius. And then we have cylinder B, which has a 5-meter radius and 3-meter height, and cylinder C, which has a 7.5-meter radius and a 5-meter height. And what they want us to find out is, are these similar solids? And in order for them to be similar, according to the rules here, they have to have the same shape and have proportional in dimensions. That's exactly the fraction, whatever you're measuring, one against the other, those fractions have to be constant. Or not constant, but the same. So let's look at the first one here. It says cylinder A and cylinder B. Well, cylinder A has a height. Here we're looking at the height of cylinder A right here. Height 4 meters, cylinder A. And the height of cylinder B is 3 meters. So if we just take the height of A divided by the height of B, we're going to get a fraction. It's 4/3, 4 over 3. Now do the same thing to the radius. Let's pick another dimension. You need 2 dimensions on each object to pull this off. But the radius of A is 6 meters. And the radius of B is 5 meters. So now what is that? That's 6 to 5. Well, 4/3 is no way proportional to 6/5. So these are not proportional. But how about cylinder A and cylinder C? Well, cylinder A has the 4 meters height. Cylinder C has a 5-meter height. Okay, so 4/5. So now let's go to the radius of each. So the radius of A is 6 meters. That's 6 right here, 6 meters. The radius of C is 7.5. 7.5. Well, is 6 over 7.5 the same as 4 over 5? Well, yes it is actually, because you can convert this. If you double both of these, you have 12 fifteenths, and 12 fifteenths can be brought down to 4/5. Okay, because you can divide both by 3 and get 4/5. Okay, so it's proportional. So cylinder C is similar to cylinder A. So they're not the same size, but proportion-wise, they're the same. One's twice as big, or 3 times as big, or half as big, but it's the same construction. Okay, for example 2, finding the missing measures of similar solids. The cones are similar. They're already telling us they're similar. We don't have to determine if they are or are not. Find the missing slant height, which is this italics L here. Okay, that's this little guy right here. It's an L, and I'm using that for the length of this slant height. Okay, so the radius of X divided by the radius of Y is equal to, since it has to be because they're similar, they already said they're similar, is equal to the slant height of X divided by the slant height of Y. Has to be, okay? So now we can form an equation. We want to know what the slant height right here, the slant height is of cone Y, where the L is. So if we write the equation, 5 over 7, which is the radius of x, 5, right here, over the radius of y, 7, 5 over 7 is equal to 13. The slant height of x is 13 divided by L. We don't know what L is. Okay, so now we've done that, we're going to solve for L. And in order to solve for L, what are we going to have to do? We have to multiply. We end up multiplying both sides, and actually do a cross multiplication to get this moved around. It's cross multiplying, but it's standard algebra, and you're familiar with it. So now we end up with 5L equals 91, because 7 times 13 is 91, and 5 times L is 5L. Once you have that with the cross product, we L, divide both sides by 5. I'll just do it. I'll say divide by 5 and divide by 5, and you'll get L equal to 18.2. So the slant height of Y, right here, of cone Y, is 18.2 yards. So there's an easy little formula to make that determination. Okay, in exercise A, we're going to do this on your own. There are 2 problems. Follow instructions, it says. Cylinder D, so imagine a cylinder they're not showing us a picture of, has a radius of 7.5 meters and a height of 4.5 meters. It's similar to the previous problem, the problem in, what was it, example 1. Which cylinder in example 1 is similar to cylinder D? So you're going to come up with that. And there's some information here to make it easier for you to find instead of going back and forth in the video. And then for problem 2, it says the prisms to the right are similar. So you don't have to make sure anything is similar. You know it is. Find the missing length and height. So the missing length and height is on the little cube in the back. The W, the length, and the width. They're calling it length and height, whatever. But they're proportional, so you can see the W goes with the 8 on the big cube, the L goes with the 11 on the big cube, and the 8 in the back on the little cube goes with or we'll call it a prism, because they do, with the 20-inch height on the back prism. Okay, so go ahead and take your time and work on it. Then when you get back, we'll try to solve these together. Okay, so now that you've had time to look this over, we're going to start with problem 1. So cylinder D has a radius of 7.5 meters and a height of 4.5 meters. Which cylinder in example 1, that's the one with the 3 cylinders that we were looking at, is similar to D? Well, I started off by writing down the D's ratios, right? So the height to radius, because that's what we had from the previous problem, height to radius, is 4.5 to 7.5. That's what they gave us. 4.5 to 7.5, and 4.5. Height to radius. And that comes out, if you multiply both of these by 2, you get 9/15. And 9/15 can be minimized, if you will, or reduced or simplified down to 3/5. You can divide both by 3 and get 3/5. Well, if you do the same thing to the other 3 cylinders on problem 1, we find out that A has a height to radius ratio of 4 to 6, or 2/3. B has a radius of 3/5, right on the ball, right there. And C has a height to radius ratio of 5 to 7.5, or 10 to 15, because you doubled both of them. And you can divide both by 5 and get 2/3. So B is similar to D. So now let's go over here and look at the prisms over here. And what we're going to do is we're going to say, well, they want to know what the length are L and W. So over here we have L and W. And we have one known dimension, 8. That's very important because we're going to need that. Okay. Since we know these are similar, that means that the volumes are similarly proportioned. Based on these numbers here, that these numbers must fall into proportion with it. So we're going to say we want L this time. So L divided by 11, that's divided by its corresponding measurement on the other solid, okay, is equal to 8. We know the 8 in the background back here, and we're going to divide it by the 20, its corresponding item or element of this prism. And when we do that, we're going to get 11L, because we have to get the L by itself. We're going to multiply both sides by 11. So we're going to get these 11s are going to cancel. We're going to have L is equal to 11 times 8 over 20, or 88 twentieths. L, 88 twentieths, is 22 over 5, and 22 over 5 is equal to 4.4 inches. That's the length of L. Now let's do W. W over 8, well, W is this side measurement here, and this is the side measurement over on this one, 8. They correspond. So it's W over 8 equals 8 over 20. 8 over 20. We're using the same back pieces. Okay? So now that you've done that, we're going to get rid of the 8s on this side by multiplying both sides by 8. So we'll have W alone. 8 times 8, 64 twentieths. Well, 64 twentieths can be reduced, I've got this in here twice, which is interesting, can be reduced to 16 fifths. And 16 fifths can be reduced to 3.2 inches. So the answer here is 3.2 inches. Okay, that's the solutions we're looking for. Okay, on the key idea A, we're going to call this here. Linear measurements, is kind of what we're talking about. Surface areas of similar solids. Before we were just talking about the length of a side, lengths of sides, missing lengths of sides. Now we're talking about surface areas of a similar solid. When two solids are similar, the ratios of their surface areas, that would be the area of A over the area of B, the ratio of the two is equal to the ratios of the corresponding measurements, the linear measurements that you know, squared. So that's, if you kind of look at it, if you were going to take two similar solids, whether it's this triangle or this pyramid or whatever it is, if you know the volume, or you know one of the volumes and you know the ratio of the two corresponding sides, you can proportion this and square it, and you can come up with the volume of one that you don't have for the other one, there's a surface area of one that you don't have, or maybe a length that you're missing. So that's what we're talking about. The surface area of one divided by the surface area of the other is equal to the corresponding linear measurement that you know, like in this case, the radius of A and the radius of B, the height of the cone, whatever it is, squared. A's measurement over B's measurement squared. So that's it. Let's see what we do with it. Okay, so let's find a surface area. So finding a surface, example 3. So we have pyramid A and pyramid B. We have a pyramid height of 10 feet for pyramid B. We have 6 foot height for pyramid A. We do not have the volume, the surface area of A. We have the surface area of B. So what did they tell us? They told us that if you take the surface area, and we want to find the surface area, right? So we're going to have the surface area over here. I'm just going to say area of A, okay, divided by the area of B. That's the ratio of that, is equal to, there goes my pen. Keeps doing that now. Excuse me for that. That's weird how that happens. I'm going to have to figure out what that is, what causes that. Then we're going to take the ratio of A over B. So we got A, 6 feet, divided by 10 feet, and we're going to square it. Okay, so, also we know, I should have put it in, the surface area of B, I can erase it and put it in actually. The surface area of B is 600 feet squared. So in order to solve this, okay, we have, I'm going to say A area is equal to, what we're going to do is we're going to multiply this out. 600 feet squared is equal to 36 over 100. So now we're going to clear and get the area A by itself. And what do we have? So we have the area of A is equal to 36 divided by 100 times 600. Okay, because you have to multiply both sides by 600. So if I multiply this by 600, I have to multiply this side by 600. And that cleared the 600 in the denominator by multiplying by both sides by 600. And now, if I divide 100 into 600, I get 6. 6 times 36 ends up being 216. So the area of A is equal to 216. And it's going to be, it's an area, right? So it's square feet. So feet square. So that's the surface area of B is 600 feet squared. The area of A, the smaller one, is 216 feet squared. Okay, key idea B here, volume of similar solids. The volumes of similar solids. When two solids are similar, the ratios of their volumes is equal to the cube of the ratio of the corresponding linear measures. So as shown here in our equation now, the volume of A, here's A, solid A right here, A, this pink one, and the volume of B, which is the volume of our blue solid over here, is equal to A divided by B. A is, in this case, is the radius A over the radius B. Could have been the height A over the height B. Okay, in this case, it's the radius A over the radius B. A divided by B cubed. The important thing is that it's cubed. Because we're in volume. Volume's cubed, surface area is square. Okay, linear measurements are not. They're just unit measurements. Okay, so there we are. We're going to probably try it in the next slide. Okay, example 4, finding the volume. So we have this original tank over here. They're calling it a touch tank. So, because there's animals in there, I guess you can touch the porpoises or whatever is in there. Anyways, we know the volume of the current original tank is 2,000 feet cubed. So it says the dimensions of the touch tank at the aquarium are doubled. They're just doubling them. That's all we know is they're doubling them. What is the volume of the new touch tank? And they give us 4 choices: 150 cubic feet, 4,000 cubic feet, 8,000 cubic feet, 16,000 cubic feet. Well, but what does the equation tell us? It says that the volume of one versus the volume of the other, right? So we want the volume of the new tank. So we're going to say V. Oh, put the V in the wrong spot. Let me get that out of there. Okay. The volume of the new tank is equal to divided by the volume of the existing tank, which is 2,000 feet cubed, is equal to the cube of a ratio. And what's the ratio? Well, they didn't give us any numbers here, did they? All they did is they told us that from the new tank to the old tank, the new tank doubled. So that would imply that the length of the tank, of the new tank, is 2 over the old tank was 1. So it's 2 that's what we're looking for here. So the volume of the new tank, I'm going to put an N here, the volume of the new tank is going to be equal to, we're going to multiply both sides by 2,000 to move and get the volume of the new tank by itself. So I'm going to have the volume of the new tank of, I could say 2,000 over 2,000, okay, is equal to 2 cubed, which is 8 times 2,000, because I have to multiply both sides by the same thing. So with these cancel, the 2,000s cancel, so I have the volume of the new tank is equal to what? And it's cubic feet, feet cubed. 8 times 2 is 16,000 cubic feet. Answer is D. Okay? Okay, exercise B is to be done on your own. They're similar solids. Find the volumes of the red solid and round your answers to the nearest tenth. So why don't you give it a shot? I mean, you see the proportions. You see the volume of 288 on the blue cone and a 12 centimeter height, 5 centimeters on the red. You don't have the volume of the red. We want the volume of the red. Same on the square pyramids. You have 9 cubic inch volume for the blue pyramid with a 3-inch side length, base length, and a 4-inch base length on the pink one or red one, whichever one that is. And we're looking for the volume of the red one. So give it a shot. When you get back, we'll do it together. Okay? Okay, I'm sure you've had time to do that. So let's go ahead and take a look at it. So what did the ratio say? It said that the volume of one over the volume of the other is equal to the ratio of some corresponding element or piece of it cubed. Well, they're giving us the height, so we know that's the ratio, where the ratio is coming from. So the volume. So we want the volume of the pink. So I'm going to say the volume of the pink, P, okay, divided by 288 centimeters cubed, cm cubed, is equal to some ratio cubed. And the ratio is, we want the pink, so the pink is on top because it's the volume of the pink. So we put the 5, the ratio component on the top of the pink one, and the 12 centimeters is on the bottom. That's from the blue one. And then when you to solve this, we have to multiply both sides by 288. So V of the pink times 288 over 288 is equal to 5 cubed is 125. And that's times 288. And that's divided by 12 cubed, which is 1,728. And when you do the math, the volume of the pink cone is going to be equal to, well, I guess I just do the math straight on my calculator, and it comes out to 125 times 288 divided by 1728 is equal to 20.8. And these are what? We're talking about cubic centimeters? Cubic centimeters. 20.8. And now for the number 2 over here. Same type of thing. We're looking for the volume of the pink one. So the volume of the pink pyramid over the volume of the blue one, which is 9 inches cubed, is equal to the ratio item, the proportion, the component, the ratioed component is, in this case, for the pink is 4. And then we're going to divide that by 3, which is the blue one. And we're going to multiply that or cube it. So that's multiplied 3 times, right? So when we do that, we're going to be multiplying both sides by 9 now, because the VP, 9 times the V sub P over 9 inches cubed is equal to 4 cubed is what? 64, right? 64. 3 cubed is 27. And we're going to multiply by 9, because both sides get multiplied by 9. So the 9's over here cancel. And V sub P is then equal to 64 times 9 divided by 27, which if you do the math will come out to 21.3. And it's inches cubed. Okay, that's it.